In my previous video, I have discussed linear algebra as a review. I have defined different type of question of linear algebra. Today also I will discuss linear algebra just as a review because I have told you many times linear algebra is very important for higher study. My first question: for every 4 cross 4 real symmetric non-singular matrix A, there exists a positive matrix P such that option 1 Pi plus A is positive definite, option 2 A to the power P is positive definite, option 3 A to the power minus P is positive definite, and option 4 EXP PA minus A is positive definite. This question is very important and very easy but conceptual. At first I will tell you, just try to oneself at first, then see my solution. Here we have to find the positive definite. We all of us know definition of positive definite is Qx equal to x transpose Ax. This is strictly greater than 0 for all non-zero x. And when A is symmetric matrix, real symmetric matrix, then A is positive definite if and only if each eigenvalue of the matrix A is positive. First option, P is Pi plus A is positive definite. Since identity is a always symmetric matrix, then P be any positive number and given A is real symmetric matrix, so Pi plus A, this is obviously symmetric matrix, and we have to find is this matrix is positive definite or not. For this, since this is the Pi plus A is symmetric matrix, so we have to find each eigenvalue of Pi plus A is positive or not. If we can to find each eigenvalue of Pi plus A is positive, then obviously Pi plus A is positive definite. For what would be the eigenvalue of Pi plus A? Here notice Pi plus A is a polynomial function. So eigenvalue of Pi plus A would be such type P plus eigenvalue of A. Since given in the question A is real 4 cross 4 symmetric non-singular matrix, so always the eigenvalue of A is not negative, eigenvalue of A is not equal to 0. That means this is non-zero number, non-zero eigenvalue. Here we have to find the eigenvalue of Pi plus A, which is actually P plus lambda A, and this is always not equal to 0. If eigenvalue of A is negative number, then by Archimedean property we can tell there exists a positive number P, at least one positive number P. For this P plus lambda A would be, this value would be positive number. That means for non-negative eigenvalue of A, always there exists one natural number P such that P plus lambda A is positive. I hope my all viewers have understood this concept easily. So Pi plus A always be positive definite. That means option 1 is the right option, and option 2 A to the power P is positive definite. For this, here given A to the power P is positive definite. Is it true? Since A is real symmetric matrix, which is real and not equal to 0, because given A is real symmetric non-singular matrix, we have to prove is a to the power p is positive definite? For this, consider x equal to lambda x, and this is true for non-zero x. Now multiply both equation by a. Then I will get a square x equal to lambda times ax, and given ax equal to lambda times x. Now put the value of ax, then this would be lambda square x. Here a square x equal to lambda square x, that means here p equal to 2. If we consider p equal to 2, 4, 6, any even number, for this I will get always one positive definite matrix. So a to the power p always positive definite. That means option 2 also right option. Option 2 is a right option. And option 3 imply is a to the power minus p. Here not p, here minus p is positive definite. For this, third we have to prove is a to the power minus p is positive definite or not. Ax equal to lambda x where x not equal to 0. And since given a is non-singular, that means x equal to lambda times a inverse x. And from this expression, we can write 1 over lambda times x equal to a inverse x. Now, multiply this equation with a inverse x, then this would be 1 over lambda times a inverse x equal to a inverse whole square to the power x. Therefore, here I have got the eigenvalue of a inverse is always 1 over lambda. So, here this value would be 1 over lambda times x, a inverse whole square to the power x. That means a inverse x equal to 1 over lambda square x. A inverse whole square to the power x equal to 1 over lambda square x. And if the eigenvalue of a is non-negative, then always a inverse square, for a inverse non-negative eigenvalue, always this would be positive. Okay. Therefore, here I have considered p equal to 2. Therefore, for even positive number, p equal to 2, 4, 6, for this, always I will get one positive definite matrix. So, similar to option 2, option 3 also right option, a to the power minus p is positive definite. My next question, exp pa minus I, is it positive definite? Exp pa minus I, here e to the power pa. What would be eigenvalue of e to the power pa? If eigenvalue of a is lambda, that means ax equal to lambda x, then e to the power ax means summation j equal to 0 to infinity a to the power 0 j over j factorial times x, and this is equal to I plus a square over 2 factorial so on times x, which is equal to x plus ax plus a square x over 2 factorial so on. This is x plus ax means lambda x, a square x means lambda square x over 2 factorial. This is so on, and this expression means e to the power lambda times x. So, e to the power ax equal to e to the power lambda x. That means eigenvalue of e to the power a is e to the power lambda. So, here e to the power pa, that means eigenvalue of e to the power pa would be e to the power lambda a. E to the power a. Yeah, eigenvalue of e to the power a is e to the power lambda. So eigenvalue of e to the power pa would be e to the power p times lambda. E to the power p times lambda. Okay. Here e to the power pa minus I. That means the eigenvalue of this expression is e to the power p lambda minus I. For positive definite, we have to prove this eigenvalue is always positive. That means if we take log both sides, then this implies p lambda. If this is positive definite, then we have to prove this is greater than 0. But p is any positive number. But here lambda is the eigenvalue of a. And given A is real 4x4 symmetric non-singular matrix, whose that means lambda can be positive or negative. For lambda negative value, this p lambda would be negative. Therefore, p lambda would be greater than 0 only when lambda be positive eigenvalue. Otherwise, this is not possible. So, e to the power pa minus I is positive definite always. This is not possible. For negative eigenvalue of a, this is always negative definite. So, option 4 is a wrong option. Only option 1, option 2 and option 3 is a right option. I hope my all viewers have understood this question easily. Now I will see one question which had come CSIR NET 2011 exam. This question also depends on positive definite matrix. The question is, suppose A and B are n cross n positive definite matrices and I be n cross n identity matrix, then which of the following are positive definite? That means which of the following matrices are positive definite when given A and B are both positive definite? Then option 1, A plus B is positive definite. Option 2, ABA is positive definite. Option 3, A square plus identity is positive definite. And option 4, is AB is positive definite? Which of these be the positive definite when given A and B are both positive definite? And we have to prove if A or B are positive definite, then we have to prove their sum be positive definite. At first, just recall what is the definition of positive definite. A real symmetric matrix A is positive definite if for every non-zero U belongs to Rn, inner product U comma AU which is equal to U transpose AU. This is strictly greater than 0 when for every non-zero vector U, then we can tell the matrix A is positive definite. And if here the given matrix is A plus B, we have to prove A plus B is positive definite. That means at first we have to verify is A plus B is symmetric matrix, then we can apply this definition. U transpose AU when strictly greater than 0 for all non-zero vector U, then we can tell this matrix is positive definite. If A and B are symmetric matrix, then we can tell easily their sum is always symmetric matrix. That means now we can apply this theorem. Given A and B are positive definite matrix, that means obviously there exists a non-zero vector u belongs to Rn such that u transpose AU strictly greater than 0 and u transpose BU also strictly greater than 0. Now we have to prove u transpose A plus BU is strictly greater than 0. U transpose A plus BU means, obviously this means u transpose AU plus u transpose BU, and since this is strictly greater than 0 and this is strictly greater than 0, that means that imply u transpose A plus BU strictly greater than 0 for all non-zero vector u belongs to Rn. That means since A and B are positive definite, so A plus B always be positive definite definition. Okay. Next question means option 1 is the right option, and option 2 imply is ABA is positive definite where given A and B are positive definite. For this, since A is positive definite, then that imply always A is symmetric matrix. That means that imply always A transpose equal to A. Here we have to prove ABA is positive definite. For this, ABA, this is just put the value. A means A transpose BA. That means now ABA equal to A transpose BA. To evaluate ABA is positive definite or not, at first we have to prove this is symmetric. Consider A transpose BA equal to P. Now transpose both sides, then the property of transpose, this is A transpose B transpose A transpose equal to P transpose, and by this expression we can tell A transpose B transpose A equal to P transpose. Okay, and since given in the question B is positive definite, that means that imply B is always symmetric. So B transpose means obviously B. That means from this expression we can tell this is A transpose BA, which is equal to P transpose. And notice A transpose BA is nothing but this is P. Therefore, I have got P transpose equal to P. So, obviously, A transpose BA is symmetric matrix. Now we have to prove U transpose A transpose BA times U. This is strictly greater than 0 for all non-zero vector U. And from this expression, we can tell this is actually equal to U transpose A transpose B times AU. Now consider AU equal to Y. Then U transpose A transpose is nothing but this is actually Y transpose. Then the given expression is Y transpose BY. Since given A is a positive definite matrix, so obviously their eigenvalue is positive, and then that implies determinant of this matrix is always positive. So AU always would be greater than 0. That means since given B is also positive definite, so Y transpose BY always would be greater than 0. That means our proof has done. ABA is positive definite matrix. I hope my all viewers have understood this question clearly. Okay? Well. Third option. Is A square plus identity is positive definite? This is very easy method. Just at first think oneself. A square plus identity. Since A is positive definite matrix, so obviously A square is positive definite, because since A is positive definite, so all eigenvalue of A is positive. So in A square always all eigenvalue would be positive. So A square always would be positive since A is positive definite. And eigenvalue of I is 1. So this is their sum. A square plus identity is positive definite by property 1. So third option also right option. Option 4 imply is AB is positive definite? We all of us know AB is symmetric when AB equal to BA. That means the matrix AB always not symmetric. So the definition of positive definite always apply in symmetric matrix. So AB is positive definite or not, we cannot tell always. So option 4 is a wrong option. That means only option 1, option 2 and option 3 is a right option. I will say another question which is also similar type but just some different. The question is, let A be n cross n non-singular matrix with real entries and consider B equal to A transpose, which denote the transpose of the matrix. Then which of the following matrices are positive definite? Option 1 A plus B, option 2 A inverse plus B inverse, option 3 AB, option 4 ABA. For this, consider A equal to -1 0 0 plus 1, because in the question has given A be n cross n non-singular matrix with real entries and B equal to A transpose. For this matrix, B equal to same matrix -1 0 1, then what would be A plus B? A plus B equal to obviously -2 0 0 plus 2. And notice here eigenvalue of A plus B is -2 comma 2. So by this example, in violate first option. Notice here A be in single non-singular matrix, also B equal to A transpose, but A plus B is not positive definite. So option 1 is a wrong option. Just recall, in the previous question has denoted A and B both positive definite matrices, then A plus B is positive definite. Otherwise this is not possible. This is example. When they are both positive definite, then their sum always positive definite. Similarly, by this example, we can contradict A inverse plus B inverse, because similarly A inverse equal to this matrix and B inverse equal to obviously this matrix, because here only diagonal along the diagonal -1 1. Then similar to before, A inverse plus B inverse would be -2 in the diagonal, -2 2, and by this construction the eigenvalue here -2 comma 2. So A inverse plus B inverse is not positive definite. Now means option 2 is a wrong option. Third option indicate is AB is positive definite. For this, consider this example for AB, then AB would be 1 0 0 1. Since eigenvalue here positive, so obviously AB is positive definite. But here and option 3 is a right option. And option 4 imply is ABA positive definite? Notice ABA means since given B equal to A transpose, A transpose A, and here obviously A transpose means obviously A transpose, and this is not be symmetric matrix. So since not symmetric, so option 4 also wrong option. In the previous question I have defined ABA is positive definite, but ABA is positive definite when A and B are both positive definite, because when AB both positive definite, then obviously the matrix A and B are symmetric. Then this is possible. Otherwise this is not possible. Okay? I hope my all viewers have understood this type of question in better way. Today I will stop here. In my next video, I will discuss another topic, as a review of linear algebra. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.